Hello and welcome. Here we are in yet another lecture. As we had before, we were continuing up our discussion about the physical issues of the hardware design. Right, so not so much in this time on the front end. We're going to talk more about the physical. So you remember way back to last Wednesday, I talked about where does delay come from in the circuits and what can we do as a designer to intervene. We had a great guest lecture by Sungwei talking about task flow and open timers. That was a great interesting content added to the course. We're returning back to that physical design emphasis today, particularly talking about power as well as design exploration, right? As you've seen in this course, right, we keep telling you to make generators. I'm like, oh yeah, add parameters, add parameters, add parameters. How do you actually pick values for those parameters? That's going to be the second half of today's lecture. But first, we're going to start off talking about power. Okay, so if you've taken out a course from me, you've heard me rant a lot about power, but the reason why is power isn't just important. It's usually the most important for almost any hardware design. So many things we can build. We could build more awesome, more, higher performance, whatever we want, if we weren't worried about power. But power is actually what's holding us back, right? So when we talk about power, there's both the actual power in terms of the issues power causes directly, as well as power over time, of course, is energy. And there's also concern about energy efficiency as well. So what is impact? Well, for energy, we care about things like how long is your battery life going to last, right? I mean, most of the things we use these days are all, mobile devices with batteries. And so that battery has a fixed amount of energy. If you can make your hardware design more energy efficient, well, you can increase battery life. Alternatively, you can, if you make your device more energy efficient, you can shrink the battery to make the device smaller and lighter, right? So obviously energy is really important. On the other hand, if you're, let's say, the data center scale, you pay for your energy, right? Energy costs money. Or if you're green conscious, energy takes carbon, right? If you're not careful. And so, there's plenty of things to reduce energy consumption. Most notably for hardware designers, right, it's about reducing battery size or increasing battery life, but plenty of impacts from energy. Meanwhile, power also has issues, right? If you burn too much power, the device can get hot. Now we know that some chips can overheat and damage themselves. So you got to prevent not reaching that thermal limit. You can, of course, have bigger and bigger heat sinks, cooling, liquid cooling, cryo cooling, whatever. But at some point, there's going to be a limit to that, right? And depending on the application you're using your hardware in, you may not be able to justify that much extra cost for cooling, right? So there's going to be some limits. In the case of smartphones, for example, right, most of our smartphones, not most, just about every single one I'm aware of, do not have fans, right? And so there's a much lower thermal budget on those devices. And yeah, guess what? People have had some phones now and then from certain vendors that do get too hot to hold, right? That's a mistake. And so power can become an issue, right? And of course, when you burn too much power, the thing gets too hot, you can sometimes have to be forced to throttle the device, prevent itself from burning itself up. Additionally, there's an interesting constraint from power which is underappreciated. Even if you have a really energy efficient device, even if you're really good to change your power consumption to prevent thermal situations, your peak power draw is still a really important constraint. When it comes to actually building out a device, even if I pull up, let's say, my phone or something, right? We all know a phone. If you think about what fraction of the mass of this phone is the main compute SoC, I don't know what it is, a couple percent, right? We know the rest of this device is going to be the freaking screen, the battery, the case, and actually a whole bunch of other chips. And some of those other chips are things for power supply, right? And so if you can reduce your peak power draw, then you can make those other chips involving power delivery and power regulation smaller, right? And a lot of these things aren't even just, digital circuits. They're actually often passives, right? Capacitors, inductors, these kinds of things, right? And so in case of a mobile device, they're really small, but we want the device to be small. So that little bit of area for those things actually matters. Meanwhile, let's say you're building data center hardware, your power supply, when I say power supply, I don't just mean whatever's in your one, box you're plugged in the server. I mean the entire process from going from utility scale power down to the appropriate voltages needed to actually power your server. There's often multiple conversions, multiple transformers, supplies, etc. Those a lot of costs. And if you can control your peak power, you can reduce the cost of those. And so it's actually a large amount of cost spent to deliver a certain power provisioning. And like I said, there's so much motivation to reduce power, right? Whether it be to make it more energy efficient, reduce power costs from provisioning, heat reasons, whatever. Cool. Questions and comments on power and energy as a motivation. Yes. I'm gonna try to repeat the question for the recording. So the question is, these big server farms to the internet, what kind of things to do? I'm gonna change the question a little bit to like shift the power load. They do a lot of things to try and keep that power load draw constant or close to constant, right? It's not gonna be perfectly constant, but um, it turns out there's a lot of reasons. Number one, if you've built infrastructure, right? Infrastructure in their case isn't just all these transformers. It's also things like backup power on site. It's also things like agreements with the utility to provide the power. Once you've gone through all that, to not use what you've paid for is wasteful, right? And so that was a shift people like Google did like 15 years ago. Is originally they were saying we want to be more energy proportional, and there's a shift in the corporate philosophy like 5 years later, saying you know what, we actually want to identify workloads that are time shiftable. That if we run these workloads, they provide value for the company, and so that way the things urgent, runs whenever it needs to run, and then we backfill in these less urgent but still important workloads in their times to kind of get a roughly daily constant power draw. What's interesting, I'm going to finish this thought and take another question. Um, there are scenarios, not just with data centers, but also supercomputers, where they have to do funny things to not break the grid. So if you're a really, really, really big data center or a really, really big supercomputer, you're burning megawatts, maybe even tens of megawatts. To suddenly take that much load on or off the grid, most grid operators cannot handle that, right? That's not what they're designed to handle. They can't just take a 2 megawatts going on or off. And so you'll have situations where actually you're forced to sometimes even if you're, let's say, a supercomputer and you just literally don't have enough jobs right now, they will be forced to put into maybe like an idle busy loop to keep that thing hot because otherwise the utility can't think that much load be taking off. Like I said, the internet companies, they're paying for us. If you pay for this hardware, you don't want to be doing busy work. You want to be doing actual value. And so, like I said, these internet companies usually have different priorities of work, and there's some work that's time shiftable that, if there's idle space, they will run them. But then, yeah, the supercomputers is a common problem where, yeah, if this big supercomputer, let's say there's a horrible crash that caused a large scale computation to die, and all of a sudden, all at once, all of your servers in your big supercomputer are now going into the idle reboot state. The problem. They actually have to do like waves of reboots to like spread the power draw. Question. Yeah, exactly right. So, or just utilize servers too, right? Independent of power, if they have idle servers, fill them up, get work on them, right? And so, definitely, definitely. So yeah, so hopefully I convinced you that power matters. Like I said, 30, 40 years ago in hardware design, I said, okay, well, how much functionality can pack into this chip? How much transistors can get in there? More thought's been going for decades. We can put freaking billions of transistors in our chips, right? The biggest constraint for any design going in is energy efficiency, right? And that's so pervasive, we kind of take it for granted, right? My CPU is going to run at 4 gigahertz approximately, right? We had 4 gigahertz CPUs literally 20 years ago, right? The transistors today are faster than transistors from 20 years ago. If we weren't worried about power, we could go faster than 4 gigahertz, right? So power matters. Okay, so how does power actually get burned? Uh, from a high level, I think of power as two categories: dynamic power and static power. Static power is power that your thing's always burning, versus dynamic power is power that's expended to actually do computation. So basically, in other words, if you do more or less computation, your dynamic portion of your power is going to change, but the static portion is going to stay the same. I'm going to spare you the circuit derivation, but the equations here for dynamic power, power is proportional to the capacitance, voltage squared, times the frequency, times an activity factor. So how might one derive it if they were to derive this? Class schema is something like, we can only take an inverter and model the capacitance on the inverter, and this model goes from 0 to 1, 1 to 0, the charging and discharging of that capacitor, right? Basically, when we think of our circuits and actually thinking more physically, right? We have our wires, transistors, etc., being put together to build our logic gates and memories and registers. Uh, we spend dynamic power whenever we charge up those values from 0 to 1, right? In order to make the voltage go up, we need to apply charge. And then later on, that voltage goes from 1 to 0. We discard that charge, and then unfortunately, we got to do it again. So charging that capacitance, which is intrinsic to these circuits, is really where the power gets expended. And so this equation has a good roadmap they know to attack, right? So let's kind of go through each of these terms. There's activity factor, which is how often something is switching. So interestingly, if you want to think of what's like the typical activity factor, it's actually really low. And I have a bias to this. I have research that takes advantage of that. That's like a few percent on the average digital circuit. Like a few percent of circuits switching, a lot of circuits not changing. And the reason why, we think about all the various paths in a big circuit, a lot of them aren't really actually being toggled. They're kind of just have some value and they aren't being active right now. And so the fact they aren't switching is an important thing for us to take advantage of to save energy. And guess what? It doesn't naturally for dynamic power point of view. If you switch a circuit less often, it's going to burn less power. The capacitance is a funny one, whereas it's the intrinsic to the circuit properties. There's this interesting trend. It's not foolproof, but it's a rough trend, which is that for a given area across different process technologies, the capacitance is roughly the same. Not exactly, but roughly. And the reason why it's kind of interesting is, wait a second, you tell me when I go smaller, I get more transistors. So each of the transistors are smaller and has less capacitance, but because of the decrease in size of transistors versus the increase in number of transistors, it kind of washes out and you end up with roughly the same capacitance. So for a given amount of area between different process generations, roughly, this is a hand-wavy thing, capacitance is similar. So as a result, from us as a hardware designer, that's going to be one of the ones that's harder for us to change. Voltage, this is the one that's actually really freaking important. So quite simply, if you crank the voltage up on your circuit, it goes faster. You crank it down, it goes slower. But you see there's a nonlinear impact on the power it impacts, right? And so because of that, if you can make your circuit be shorter in terms of delay, fewer FO4s from the last lecture, you can turn down the voltage. And because you turn down voltage and it gets a quadratic reduction, you can really save some energy. So to kind of give you some rough numbers for this, there's a famous paper from Anant Panchajaka-san from now nearly 30 years ago, which is kind of motivating to push the parallel. And he basically in that paper showed, hey, if you have like a certain functional unit, let's say running at a certain frequency, and it burns a certain power. Now take that same functional unit and make 2 copies of it and run them at half the frequency. Now if you run them at half the frequency, each functional unit has half the throughput, right? But if you have 2 of them, you've now, if you have enough parallelism, of course, you've restored the throughput. So you have the original design running at 1 frequency, and the second design, which is twice the area, but running 2 copies of the same design, but half the frequency. And so you might say, okay, well, why would you do this? Well, because the other one's running at half frequency, you can turn down the voltage. Because it's quadratic, you maybe could even half the voltage, which means each one takes a quarter. 2 times a quarter is a half. So in other words, you've had the raw power consumption for the same throughput. So you've traded area for power in this case, right? And also it's worth remembering that if you change your area, you also change your power density. So things like cooling are often depending on power density. In this case, I just told you you're doubling your area and you're halving your total power. That means you actually have 1/4 the power density. So that actually could be a very different landscape. Those are some very, approximate numbers. It gives you a sense for what's going on there. So being able to run slower and lower the voltage is really, really nice when you can do it. Okay, so let's talk about what we can do as actual designers. How can we intervene here as architects or hardware designers? So number 1, activity. If we can reduce this toggling activity, we'll come back to this one a few times in today's lecture, we can save power, right? And that we can also be very deliberate and put things to sleep. If you're not switching, not gonna burn as much power. Guess what? Make the design smaller, less area. That's gonna reduce our capacitance, right? That's less to charge and discharge. And then when it comes to frequency and voltage, well, this comes down to what is our target performance. And for our target performance in our current design, which has a certain delay, we have to run at a certain, voltage to meet that frequency, right? So if we can, make a design that needs to operate at a lower frequency, we can lower the voltage. Or if we can reduce the amount of delay in our critical path, we can reduce the voltage we need to meet that certain target frequency. Cool. Questions? Let's keep going. Okay, so productivity stuff. What can we do to save power, right? Turn things off, right? Um, so there's two types of turning things off. Uh, the big one, the hammer is power gating, right? There's an entire portion of your chip, you don't need it for a while, and just turn the whole thing off. So when we say power gating in this case, we were literally affecting the power to that portion of the chip, right? So it's not just that we aren't using it, there's not even, voltage flowing in there, right? Um, so you do power gating. That's of course very heavyweight, right? So take a certain latency to turn it off, set a certain latency to leave, but sometimes it's okay, right? If I'm right on my phone, it knows it's, not, the camera's not being active. It can probably turn off the camera processor just fine, right? Save that power. Um, Meanwhile, there's something that's also called clock gating, which is recognizing that in your design, your clock actually burns a non-trivial fraction of the whole chip's power, right? And the reason why is your clock is actually one of the few things that has an activity factor of 1. Like, so you think of a wire that's randomly has a random value every cycle. The activity factor is actually 0.5, right? Because there's actually a 50% chance you're not going to change, right? You're going to be, versus the clock is both 0 and 1 every freaking cycle. So actually it's like an activity factor of 2 in a way. It's like charging, discharging, it's so much. And so as a result, clock can burn a lot of power, right? And so guess what? If there's portions of your design that you're not going to be using right now, or at least for a little short amount of time period, you can turn off the clock in the clock tree. So, so that's the portion of the thing that's being toggled so frequently for the clock is reduced, right? So this can actually save quite a bit of power. And what's interesting about this used to be like, 20 years ago, this was a cutting edge, super sneaky, cool expert trick. Now, a lot of CAD tools can do this automatically. They recognize, oh, wait, here's a register. I can do some clock gating for automatically. And that way I can save some energy in this. When it comes to clock gating, the emphasis is on registers. And the reason why is that, logic gates and typical CMOS don't take clocks, right? So the reason, of course, is if you can clock gate the registers won't change your outputs. And if your outputs aren't changing, how much of the logic downstream of these registers also will not change, right? So you're kind of reducing their activity too. So you only need to control the clock going to the register and kind of the same impact. So what does it matter from us from a designer's point of view? Where we come in is we need to make it possible for the tools to put in the clock gating. And it's actually a really interesting spot where if you didn't know about this, you might not come to the right conclusion. So normally if it's a hardware design, you think, okay, yeah, I'll use a register. And maybe there's a time that register is sometimes a don't care. Okay, fine. Register is sometimes a don't care. Well, it turns out those are the times when it's a don't care, it would be great to be able to power gate it. But for the tools trying to preserve the semantics of the language, they can't make that intervention because they don't know it's a don't care, right? And so one way to enable that is actually if you have a register with a write enable on it, reg enable and chisel, but other language something similar, and you make the register turned off once it don't care, the disenable's deasserted, that helps it actually enabled later on to go do clock gating, right? Otherwise, clock gating wouldn't necessarily be possible, but when you have that situation, then you can, right? And so that's actually kind of a cool little trick. So yeah, so don't care if you think the value matters. It doesn't matter, but if you put a register enable and when it's don't care, you actually get the tools help you help later on. And this helps. This can be definitely worth doing. Cool. Yes. Question. Can you elaborate more? Yeah, great question. So in addition to turning the clock off, what if I only just want to run a certain portion of the chip slower? That's the next topic. Yes. Yeah, these are kind of like the turning things off theme, or let's just cut power, cut the clock. Cutting power saves the most energy, but it takes the most latency in and out. Cutting the clock can save some of the energy, right? One thing I did not talk about initially was, like I said, the static power is something just non-trivial. Power gating can help you save static power, right? Because power gating, there's no power flowing into that portion of the chip. With clock gating, you're going to be reducing the effective activity factor. That impacts dynamic power. It does not impact static power. So if you have that leakage current in your static power, that's still going to be getting you. And so Both these tools are not just commonly used, but have to be used, right? Both for smartphone chips and server chips, they have to do all this, right? In 2024, you want to build a chip, you have to do these. You can't ignore these. Otherwise, it's going to burn up its energy too fast. Cool. Questions? Okay, so then back to that point. How do I manage processing speed, right? Where even if your device is capable of a certain um, performance level, doesn't always mean you need to run at that speed, right? So for this lecture today, I'm kind of taking two emblematic philosophies. These aren't the only two approaches, but these are kind of the common approaches. So one is to recognize what performance you're targeting. Maybe for the sake of argument, you can imagine something like, let's say, playing a video to a user. So you have like a periodic deadline. You get a certain amount of work done by that deadline. You need to render the next frame, that kind of stuff. And so what can you do? Well, you can, find out the deadline is, turn down your frequency just to the point where you barely meet the deadline. And of course, by doing so, you're reducing your voltage. So by running slower, you're going to use up less dynamic power. There's still some static power burned. That can work well. Interestingly, there's also some situations where the best thing to do is actually to go fast and then turn off completely. And so what matters, of course, is how much energy are you burning total, right? And so depending on these constants, how this works out in your particular scenario, either situation can be more efficient. This is why both techniques are commonly used, right? Sometimes race to halt is good because you can turn off and you can save that static power portion. Other times, the reduction in dynamic power by going slow is so great that the static power is such a small fraction, it's better to do crawl to deadline. So both philosophies are common. So I'm going to kind of elaborate on the two in the next few slides. Kind of want to get the idea across right in the beginning. So like I said, so going slow. Turn your voltage frequency down to meet that target. And I said, as we talked before, we turn the voltage down, you go slower, but there's a super linear power benefit, right? So that's why you do it. And that's, of course, setting that intelligently, changing the voltage with the frequency at the same time. That is called dynamic voltage and frequency scaling. So yeah, this is something that's been, now a standard technique, but 10, 20 years ago, it's kind of considered very exciting and new. You change the speed of your circuit. And it doesn't need to be the entire chip, right? You can change portions of the chip at a time. And in theory, you can change the clock and the voltage independently. Depending on design, they either are or are not independent. Sometimes you'll have more granular ability to change clock than you do for voltage, because voltage requires a voltage regulator or something. But it depends on the design. But the key point is that this is definitely a knob you have, right? It's how fast you want the circuit to operate right now. And if you do things right, i.e. reduce the voltage, when you turn the frequency knob down, you can also save power. And so the alternative instead, of course, is to get rid of that static power by going really fast and then going in deep sleep, right? So you want to go as fast as you can and complete. So this is kind of an interesting thing where a lot of times people think that, in order to be energy efficient, you need to be, really slow, really low power. Sometimes actually just zooming through to work and then turning the thing off is the most energy efficient thing you can do. So it depends on the details. When you think as an engineer, you always got to run the numbers and see what makes sense for your scenario. A lot of devices, if you look through every single system throughout the entire device, you will see them doing both. It's not even just a single, choice applies globally. No. Within, something as complicated as a smartphone, you see different portions do different techniques. Cool. Yes, question. That's a great question. So, if I have a mobile device with a screen, um, isn't the screen a significant amount of power? If I do race to halt, can I turn the screen off? Um, so the answer is yes, or maybe it doesn't matter. So a few things to remember that there's a lot of different components in a device, right, in a product, right? And so if I'm doing race to halt, I may be doing race to halt for the SoC, But you're right, maybe the screen is on the entire time, but the SoC itself is being power cycled, right? And so by turning the SoC partially off, not even completely off, but partially off, I can save some energy. The other thing is, a lot of phones now have, variable refresh screens, right? You don't need that 240 hertz all the time, right? You can crank that down. If someone has a screen, they're like not changing anything, right? What you don't need to run 240 hertz, save some energy, right? So this is kind of the thing. Everything's being more dynamic, more scalable, more adaptive, and to do that. And like I said, the sleeping is actually really, 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 really important. Like I said, many years ago, I was at Nokia Research as an intern, and this is a time period when Intel was very bitter about their Atom not being chosen for smartphones. And it showed they didn't understand the dynamics of the situation. Because they were saying, oh, we were told, smartphone processors had to be under a watt. Our Atom can run at a watt. So we know. Why aren't smartphone vendors using our processor? And the smartphone vendors were saying, well, the ARM processor you compete against also burns a watt. However, when it idles at 80 milliwatts. Yours idles at 800 milliwatts. Guess which one we're going to use, right? Because it's going to kill the battery overnight or like instantly, right? So sleeping and idling are extremely important on your smartphone, believe it or not. Even when you think you're watching a video, which to you seems like an active action, right? Like I said, it's going to recognize, oh, wait, this video is only 30 frames per second. I can scale down the frame rate. It's like, oh, wait, I already rendered this frame. I have 30 milliseconds to do whatever heck I want. So maybe it's actually sleeping between each frame for all you know. When it comes to your radio, it's also going to be turning it off between when you're actually saying bursts. You know when your next time slot's going to be to communicate in the radio. Between that and the next time burst, turn the radio off, right? So the modern design is constantly turning things off or slowing things down when you don't need it. And so these are kind of two philosophies, right? You turn it down slow or you turn it off. Depending on what it is, you can do either one. This is the modern energy-centric world we're in. Yes, I saw another question. Yeah. Yeah, great point. So hey, wait, didn't I say that peak power has a certain cost impact? So would race a halt by having a higher power consumption cause issues? It definitely sets some cost, right? Like I said, there's like the peak power system needs support, sets a cost parameter. Presumably, your device wants to support the level of performance some of the time, which is why you're paying that cost for that power infrastructure, right? Um, and thus, that's why you have that capability already there. You've already paid for it. But no, if you haven't already paid for it and now you have to increase the size of the power structure in order to race the halt, you might think twice about that because that's additional cost. Like I said, as designers are always thinking so much about, the SoC, but I said there's so many other things inside the entire product and things like I said, a lot of times these passives, right? Like literally inductors and capacitors and the number of those and how big they need to be and that kind of stuff is impacted by stuff like your peak power draw. Cool. Okay. Great questions. So yeah, so those are kind of two philosophies for power management. Actually, that concludes the power portion of today's lecture. Maybe I'll pause for any more power questions before we go on. Okay, well then we can still, this thing's dying. Okay, there we go. Um, like I said, all quarter been saying, we're going to build generators. We're going to build generators. We're going to build generators. But then how do you set those parameters, right? And so the process of choosing many possible designs and honing your design, and this concludes both actual new designs as opposed to just setting parameters on a generator. The whole combination that's called design space exploration, right? How do you pick which is the right design? So yeah, this is what we've been pitching all quarter, right? By having generators, it makes us able to consider more designs. And that's kind of the point. It's not just about getting one design working one time. With generators, we can make many designs, and thus hopefully we can pick the knobs and tune it to be better fits to our particular application. But of course, if you want to pick the best one, what's the right one? Well, how would you do that? What metrics do you consider? So that's something to consider for what you actually care about. And then, which is a very common engineering challenge, what happens if there's not just one metric to optimize, but multiple metrics? How do you trade off between different metrics? So that's what we're going to talk about, this small design exploration lecture for today. And so sometimes you might hear me or others contract design space exploration as DSE. And so that's, get that notion out there. Okay, so when it comes to metrics, the first three we've seen all quarter, right? We know about power, performance, and area. Yeah, those are the classic PPA metrics. Power, we just covered it, right? There's your average power versus your peak. Performance, latency versus throughput, we know all about that. Area could not just be how big your compute portion is, but perhaps how much I/O you need to get off the chip or other components, etc. So those are all big impacts. But then there's actually a lot of other metrics we don't often quantify, but we should, right? things like usability, security, or things that your manager will care about, things like manufacturability, right? Even if you have a good design, if it turns out your yield is very low for manufacturing, that increases cost, right? So can you change your design to be more manufacturable? Super important. Testability. Okay, let's say they manufacture your chip and you want to see how quickly they can see if it's correct or not. Also important. Or in some cases, you even care about fault tolerance, right? How well can my design work under some portions of failure? So there's a lot of different metrics. Are there any metrics I missed? Anybody have any other ideas, things to consider? Sometimes if people add one, add just list. So I'm asking in case I keep forgetting. Some of these metrics came from prior students. Okay, cool. Yeah, but you see the point of the slide, right? The point of the slide is a lot of metrics out there, right? And for a given application, it's not just one metric. You usually care about like optimize this metric, but don't forget what's the other metric, and then I care what's the other metric too, and like this one's got a constraint, etc. Yes. What? Maintainability. Definitely an important attribute of a product. I'm curious how it impacts design space. I don't know. It's interesting. I'll have to figure out that one. Was another suggestion? Reusable. Oh, that has to go in. For this course, yeah. Great suggestion. We care about reuse, right? That's one of the themes. So yes, definitely. Like a plant. Okay. Maintainability is also important, but it's like I don't know how that impacts me as a designer, but reusability, that's you optimizing for cost for your company in the future, right? If I design this thing in a certain way now and make next year's product cheaper to design, I've done a good thing. I'm doing a hand motion for what I mean by security only because, yeah, I'm making it very broad, right? You can imagine security is an extremely complex problem, right? You have your architectural level concerns, things like your side channels, your covert channels. You have just what level, perhaps quite bluntly functionality wise, like, oh, do you support blank encryption, right? Um, and there's also sorts of more devious things like power side channels, or what about somebody tapping certain wires to peak certain things, right? And so it's a really broad topic, and I just kind of use this umbrella to catch all the things. So not all these things are under Chisel's control. Yeah. So not all these things are under Chisel's control, but these are things that you as a hardware designer may be asked to consider, right? And so your manager might tell you, yes, your chip needs to not have, overt side channels between different users and support this type of encryption or something, right? Um, but yeah, there's lots of tools we're doing to like obfuscate circuits. So it's always harder for someone to take apart your chip to figure out how it works and that kind of stuff. There's a whole industry for that stuff. Cool. Okay, so metrics are goals, right? Then there's your parameters, right? Now, like I said, this course I've been telling you, use generators to get parameters, right? Um, and there's two flavors of parameters. There's what I call external parameters, which is things people outside your generator see, like, oh, like how many ports does it have? How wide are these ports? That kind of stuff. And there's things that are parameters, but they aren't as externally visible. Things like how much parallel is internal, how much, hardware is there, how big are certain internal buffers or queues. Maybe you have a really sophisticated generator has multiple fundamental different microarchitectures, and thus you can choose different algorithms in turn there, or maybe different topologies. Had a network generator before, right? So these things kind of all come together on that front. Sure. Okay. So then, uh, given the metrics, parameters, how do we actually go about evaluating things? Well, um, normally if you take all of your parameters and consider all combinations, that's typically too many options, right? If it's not too many options, eh, run it, see what happens, right? And for all those options, some of those you can metric wise, you can quantify pretty easily. Things like area, power, those are easy to quantify. Some things like security, depending on what you mean by security, it might be harder to numerically quantify or at least do direct analysis. Um, so this is the situation we have. We have this massive design space. Let's assume we have enough generated parameters that we can't just run them all. So then what do we do? Well, we got to start trying to, make sense and tame it down, right? And so number one, you can't consider all 10 metrics, right? You ask yourself these metrics, which are these most critical metrics versus which of some are just nice to have. Additionally, a lot of these metrics sometimes, rather than being something to optimize and maximize, it can be something that's just a constraint. Like in this case, power under a watt. For security, perhaps, supports X, cryptographic protocol, whatever it is. So it gets turned into a constraint rather than a metric to optimize. So as a result, you can probably take, your 10 metrics in your slide and maybe turn, let's say, like 4 of them into constraints, and then 2 of them ignore, and you have 2 or 3 you're left with that are actually things that we really want to optimize and really improve. That's going to determine how valuable your product is, right? With the remaining metrics, like I said, if you have multiple metrics, it's hard to pick which one to do. So sometimes there's a clear preference, right? Like I want to get the best performance I can first, and then power matters second, right? But if there's not a clear precedence order and you have metrics that potentially could be equivalent in their importance, then you do a trade-off, right? To figure out how much I improve one relative to the other. We'll come back to that in a second at the very end of the lecture about how to kind of reason about that. Okay, so number one, get serious about what your metrics matter. When you're doing your projects, even though you folks don't have a back-end design flow, you still may have some notion of what metrics matter to you. Then in terms of parameters, right, like I said, all combination of parameters are probably not possible. And so you got to be a little bit more judicious, right? So maybe you might figure out how there's some parameters that are technically independent. And guess what? They're independent. I can kind of explore one parameter at a time, right? I don't need to change. I don't need to try all combinations, right? Other parameters might actually be paired and should probably be changed in lockstep. Things like, matching throughput of a producer and a consumer. Some parameters are more impactful. Perhaps you want to change really big things like, let's say, number of cores in your design. And then you can change smaller things like the internals of the core or something, right? And so this is kind of just the ground rules for getting started. We're going to fine tune both of these things in a second. I'm going to pause here for any questions so far. Okay, so then let's say you've, set your ground rules for your design. Okay, you know which metrics are the ones that matter, which metrics you've turned into constraints, of the parameters, some idea of which ones you got to turn. But like I said, there's still too many things to try all combinations, right? So now if you try to turn this into an optimization problem, a lot of times people want to solve this in math. Math can be great. The problem is a lot of these metrics, if you look at the results of that metric across all possible designs, it's actually a non-convex, meaning it's not a simple, solution to find it. And so thus you could try brute force, but it's also not always possible. So you do a few different things, right? Unfortunately, this is something that may change soon, but for now, there's a lot of human guidance, right? You understand how certain parameters are going to impact certain things, and you're going to try and give it a good, framework or skeleton to get going. And then you may still use a lot of other algorithms to help you try to explore it more finely, right? So there's classic algorithms like branch and bound, dynamic programming, randomized search, stochastic gradient descent, things like simulated annealing. Of course, there's more sophisticated algorithms, things like genetic evolution, machine learning. There are so many papers on design exploration frameworks. There's a bunch of them out there. You may find a framework out there you like for your project, but I'm suggesting that you probably, as a human, at least take some control of this problem, and then get the assistance of additional productivity having a framework kind of doing the fine-tuning. Like I said, if you can determine some metrics are independent, you can sweep that one parameter. Even though you maybe have 100 parameters, if you only sweep one parameter at a time, then perhaps the number of design points isn't too many for you to actually run. And it's simply a matter of just running more design points. Well, guess what? One thing is this course, put computers do the work, make tools do the work, right? So yeah, if running more cycles on your cluster gets you a better design, that's a good outcome. That's a good place to be. So one thing that comes up a lot in the research is, actually pushing a design through the entire tool flow takes a long time, a lot of resources. What if I, didn't do that and use the model to kind of quickly assess the design space? The answer is that can work, but it's not guaranteed to work, right? And as you can imagine, it's just completely dependent on how good your model is, right? And so, like I said, my attitude is, hey, for a lot of things, maybe not an entire chip at a time, but like portions of a chip, you can definitely use generators and just try all the options. And then, because trying these other options doesn't require as much human effort to change the design option. It just is more time for computers crunching. So let's do that. And one thing else comes out is that this kind of notions people often have historically, okay, I'm going to do analytic models, do design situation on an analytic model, and then cope the Verilog and I'm done. And it's like, that's not really guaranteed to get you a good result. And so the whole point of this course and Agile, the approach is, you know what? Let's get something running, see how close we are, and start, adding parameters, tweaking parameters, and kind of see if we can fine tune to reach our target, right? And having the ability to kind of change your design to match, like I said, may turn out what you thought would be a bottleneck in the beginning. Once it's pushed through tools, may not be the bottleneck, right? Maybe something else. And so, yeah, the Agile approach of getting something running and all the way through a tool flow, not just running functionally, but actually pushing through physical design, seeing how much things cost, where your bottlenecks are, then going back and iterating and improving. That's where we can really get the quality improvements of Agile. Cool. Questions, comments? Let's try an example. All right, let's say you took your homework for, your matrix multiplication, the one you did the code reviews of your colleagues for, and we wanted to try to, do that a bit more rigorously. So what can we do? Well, let's kind of appreciate what metrics are available. So we know external parameters, right? How big the matrix is working on, and is that a rigid or a flexible constraint, right? For homework, it was always the same size matrix. But what if you had a big hardware accelerator and a liquid one size matrix? That may or may not be okay, right? Maybe you want to be more flexible. Alternatively, for performance, right? We had this notion of this parallelism knob. There were some other knobs. How is the interface thing done? We kind of started doing this, multi-cycle exchange on the MC version. So as I said, these are the external parameters. The internal parameters are things like, the architecture, is it 1D, 2D, systolic, etc. How much, buffering, caches, scratch pads, etc. you have inside there, parallelism. These are the internal parameters. And of course, how might I measure this? Well, let's say we ignore the parameters for now and only do PPA. Well, then sure, there's your power and area and performance, right? So these are all kind of things we've been talking about all lecture, and there they apply to that design. So how does it actually play out? Well, what do? First, we got to, identify what the problem details are, get that ironed out. So one of the things you may not have appreciated until you're doing the project yourselves is that for all the assignments so far in this course before the project, I tried to in a README to specify the details, right? I often even gave you skeleton code so you can understand, okay, here's the interface, here's what it needs to do. When you're solving an actual problem, that's your job, right? And as you're learning from the project, like sometimes it takes a little bit more effort, right? So number one, specify the problem, the external parameters, sure. Two, okay, figure out what you're gonna build this with, what kind of things in your budget, if you have to use offset memory, what kind of bandwidth and interface you're talking, that kind of stuff. Now, even though I told you a second ago using an Agile process, I still think there's some room for analytic models really early on, but I want to emphasize, this is, an afternoon's worth of work with a whiteboard, right? It shouldn't be a super sophisticated thing you run for a long time. It's just back envelope kind of math. Is what I'm hoping to build buildable, right? Am I trying to build a gigantic thing in an old process 100 millimeters squared and it's not going to fit? And I should know that, right? And so that kind of gets you realize, kind of a sanity check what you're doing. So ways you might do this, for example, is looking at similar chips that have similar functionality and kind of get a sense for what kind of resources they took to get that performance, and considering what your performance changes are, you can maybe approximate, if you need more or less resources. Other times it's completely novel for the first time. It's going to be kind of hard to do, but you still might be able to kind of bound it. Okay, you can say, I want to run at this performance rate. I know for this workload to get that performance rate, I need to have a certain amount of memory bandwidth, and you can kind of start seeing those kind of plays together, right? Okay, is my performance rate commensurate with memory bandwidth? Or let's say, for your particular problem, I need a certain amount of on-chip memory to reduce the off-chip memory communication. And okay, for the technology I'm considering, do I have enough budget to have that much on-chip SRAM or whatever, right? So you can still do some early analytic stuff, but then yeah, go ahead and code it up, right? We've done this, right? Close the loop, write up some, your model, write up the chisel, get it working. Here's the key part. Get the evaluation set up early. We're not just testing, but the physical flow. So you start measuring how you're doing. And things start getting more mature, start sweeping parameters, seeing how trade-offs are applying, and you start seeing certain trends. You might get ideas for how you want to turn those knobs and how you might want to do things. And then reflect, right? What you've learned, change the architecture, add knobs, etc. And you kind of keep repeating 4 through 7 over and over again. This is the part where having an agile development flow and having generators really pays off, right? If you only get to go through this loop once, you can see there wasn't a lot of early on planning, right? So the chances are that, this design is exactly the right design. not that high, right? A water flow approach would probably try really hard to have a good plan in advance, but I'm telling you from experience that you can't always know in advance, right? You don't know how big certain things are going to be. Trust me, you want to instead keep revising at the back half of this, right? Which is what you do for an agile approach, right? You can get something running and go for it, right? And as I said before, a common quip about agile doesn't mean you have a plan. It just means you are able to change your plan easily, right? So you should definitely have a plan. That's what step 3 is. But then don't be afraid to go ahead and revise and tweak. Cool. Questions? Okay. Then the last thing is back to that point I said I would talk about, which is how do you optimize multiple metrics at the same time? So to explain that, there's this notion of Pareto optimality, and I want to get that idea across, right? So let's say we have 2 metrics we care about, X and Y. And let's say, if I think of today, higher is better for both metrics. So these are a variety of design points, and we plot them all on a scatter plot. This is, of course, a cartoon, but it gives the idea based on these 2 metrics, right? So what's interesting about this is we start seeing that certain metrics have certain benefits, right? For example, if we compare these 2 design points, this one is better than that one, metric X, right? So if I care more about metric X, I should probably pick this one. However, if I care more about metric Y, this one is technically a touch higher that way. Yeah, question. Potentially. Let me double check that. Um, Correct. Yes. Great point. Yeah, I'll put this for recording. Yes. So for today's lecture, I was glad to be corrected. The metrics are better when they're smaller. So yeah, so you can see, as you can see, which is going, you want to be on a Pareto frontier, right? So this blue highlighted portion, these green points, these are the points that are good, right? Where in other words, take this point for example, or maybe it's better to take this one over here or something. If I care about metric, any one of these metrics, you see, in order to improve, I have to worsen the other metric, right? So, oh yeah, sorry, the blue would remind you to lower is better. That's a good point. I made this 3 years ago and I've already forgotten. I feel so bad. But yeah, so you can see that, yeah, we want to go this way, and it turns out you can't get everything you want, right? When we have the lowest on X, Y is blowing up. Now, maybe you might say, you know what, I want to be a balance of both. I want to be low on both of them. Perhaps these knees in the curve do occur. But yeah, in this case, let's say to improve Y, this is lower on Y, but I had to give it something on X, right? It's a trade-off. And what's surprising is in engineering, how often it's not just this property emerges, but the actual shape of this curve emerges. Where you get enough design points, you actually see these curved frontiers, right? So if a point is Pareto optimal, that means on a given metric you care about, no point is better on that metric without being at least worse on another metric, right? So in other words, this point is Pareto superior to this point, right? It's both lower on both metrics, so you don't want that, you want this. And so you kind of see the benefit of Agile, right? If you're doing waterfall and you only get to build one design, what are the odds you're right here? Maybe you are right there, but you'd rather be here, right? So having the ability to change where you are on this curve is really important. And so the only way you can know where you are in this curve is to actually have a lot of design points, and you actually can prove, you know what, here's a lot of freaking design points. Here's the emerging Pareto frontier, and we're on it, and we're going to consciously choose where we want to be on this design curve. Cool. So to drive home the Pareto frontier, unfortunately, I don't have these numbers from industry, but I have these numbers from 2 academic papers I wanted to share. So for one, this is a paper from Sophia Shao. You see, yeah, she generated a ton of design points, right? But you still see that thing we just talked about. In this case, we're looking at execution time on the x-axis, so of course lower is better. And power on the y-axis, where lower is also better. And we can see, yeah, you want to be here. You don't want to be here, right? Right? And listen, you don't know you're here until you have the other 200 points, right? And so this is why it's good to have the ability to kind of do design inspiration. And so, yeah, you want to be down here. And so in this case, she's looking at various trade-offs in terms of, changing. So one of the things that comes across with these design inspiration scatter plots is because you're turning so many knobs, how do you visualize this, right? Because you have only so many colors, only so many point shapes. And the answer is this trial and error. I've had grad students make these plots, and they're like, oh, I'm like, just try different dimensions and see which one you like. Because like sometimes you will or not see certain trends. So in this case, they're changing color and shape in lockstep, which is a good practice to be grayscale friendly for papers. And you're seeing, yeah, depending on the bandwidth, you kind of have certain regimes, right? So, if you have a lot of bandwidth to your cache, sure, you will be very fast, but it's going to burn more power, right? If you have very low bandwidth, it's going to be the slowest, but it's also going to be the lowest power. And you can see these other parameters, which are not labeled, as clearly are affecting various things. You can see like L1 size, for example, takes more power, static power from your SRAM, but will make you go faster. Things like blocking, etc. So I'm just showing you, here's an example of, a real world design acceleration kind of curve. And yeah, is that parameter frontier. You want to be considering these points. You don't want to be over here. At that point, you're just burning more power and taking more time. Yeah. So in this particular paper, actually very fast. So this is the research now, which, oh my gosh, I'm dating myself. As you can see, it's 10 years old. And so the contribution to this research paper, which is called Aladdin, was to characterize a technology. So in other words, you have your PDKs, you have your ASIC CAD flow. It would run a variety of designs through it, look at how much area and power that took, and then it would try other design variants, and using that model, compute the area and power without actually doing a full synthesis in place and route. Decent. Yeah, so that was kind of the interesting takeaway from this paper was, like I said, the contribution intended was, use my tool Aladdin to do design exploration for you, where, you don't have time to like try a zillion options. In this case, the design variants came from HLS flow rather than from a generator, but it's a similar principle. For me, as a person reading the paper 10 years ago, I was impressed by, oh my gosh, these ASIC CAD flows are, approximable to a reasonable extent by a dot product, right? I was literally like, okay, how many exponent do you have? Okay, has this weight, and then you just simply take a dot product to combine them all, and so it actually was modelable, and that was kind of the contribution. So yeah, so I don't have the numbers in front of me. You can follow this link on the paper to go read it, but I believe there was some validation of the model, and I think there was some amount of error, of course, but it was smaller than you might think. It turns out, doing a full place and route, synthesis, place and route, and all that kind of stuff is overkill for early stage design exploration, right? Like the odds of the point here is going to jump over here if you do a full run maybe isn't that high. Maybe, not guaranteed technically, but so to do the early run of like 500 points, maybe do that really fast modeling. And then when you get down to your, most promising 30 points, when you start doing the full place and route. Cool. Other questions, comments? I have another plot from paper, actually. Another pre-optimal plot. This one, to your point, is actually also somewhat model-driven. So it's not completely synthesized designs. In this case, it's architectural. So this is taking a little bit more of a processor-minded viewpoint. And what this is showing is, okay, if I build a processor, I can build it, in order, out of order, familiar. How wide is it? 1 wide, 2 wide, 4 wide. And you can crank the frequency, right? You have that frequency. And so you change the frequency, you change the voltage. So a given design, you kind of can play with that. And so what's interesting is you look at this sweep of designs, you say, okay, which is the best core to use? And the answer is, it depends on where you want to be on this curve, right? You can see that for any given design, it has its heyday, right? For a really small energy consumption, turns out the in-order 1 wide, unsurprisingly, does pretty good. If you want really high performance, even if you're willing to spend a lot of juice, not only does some of the in-order cores not even reach that fast, even when it does, you're actually better off using the big out-of-order core. I was saying that earlier, right? Sometimes going fast and big is actually better than really cranking frequency on its in-order core. So yes, if you trace the underside of this curve, because in this case, down is better, but right is better rather than left for performance. Like I said, you see different processors kind of have their moment. For a given processor, depending on what you're pushing frequency, it's kind of a linear regime, and then it kind of blows up on you, right? And so you kind of maybe want to avoid a blow-up regime. But it's kind of just very pleasing, right? This data. You see, oh yeah, if I want a small amount of energy and I don't mind about performance, the best thing I can do is 1 wide in order. If we want a bit more performance, a 2 wide in order is a really good sweet spot. Technically, there's a small window here in which the in order 4 wide wins. Meanwhile, if you're going to go out of order, you should go at least 2 wide. The out of order 1 wide, let's see if we can find that line. It's this one. Yeah, it never pans out, right? If you're going to pay for out of order, get at least two, go at least two wide, right? You get some bang for your buck, right? And you see the four wide, yeah. If you have a certain performance target, that is going to be better, right? The four wide is going to be lower power than the two wide, right? Um, so I just two plots from papers to kind of show you this pre-optimal concept in theory. Whereas like number one, you want to get a lot of design points, right? And so both of these papers are from 2010 and 2014. So back then they're doing models and other ways to summarize things. Um, but guess what? In the chisel era, we can just turn parameters and chuck it at tools and let tools crunch. Cool, yeah, definitely. Yeah, you should read a paper to see how they modeled it. I suspect it definitely involves an architectural ISA simulator. It definitely involves a simulator for the performance characterization. For the energy and area calculations, that may be a model in a simulator. I'm not convinced how that's done. But like I said, I'm just showing examples of pre-optimal curves, right? This idea across that, like, if you're just one design point, you don't know where you are. You want to see a lot of alternatives, and depending on what you need, there'll be different right answers, right? So you want to be aware of what those trade-offs are, and any good engineer is aware of trade-offs. So like if some engineer says, "Oh yeah, we're going to do this thing that's better or it's the best," I'm like, "Okay, what if I want to do a trade-off?" No, no, no. If you're a good engineer, you're always aware of the trade-offs because that means you're pushing the limits of everything you're doing, and in order to do better, you got to give something up. If you can just be better without giving anything up, that's either one heck of a breakthrough or you aren't a very good engineer, right? Like you need to be constantly, for all of your metrics, maxed out and doing trade-offs. In order to improve a metric, you got to trade something else back. Like, okay, you want me to go faster? It's going to cost more. You want me to do this? And so that's the point of these two lectures, two examples. So this is also one of the prettiest plots seen in a paper in a while. Cool. Any other questions or comments? Okay, sounds good. Thanks, folks.